Hello students, today we are going to study kinetic theory of gases. In the chapter of kinetic theory of gases, we will study various assumptions made in ideal gas model as well as various gas laws like Boyle's law, Charles law, Gay-Lussac law, Avogadro law, Gram's law of diffusion, like that. Okay, so let's start with the Boyle's law. According to Boyle's law, the pressure of a gas is inversely proportional to its volume when temperature of the gas remains constant. This is the Boyle's law. And the graph of pressure and volume is a rectangular hyperbola. And the graph between pressure and volume, 1 upon volume, is a straight line. So when we want to apply Boyle's law in numerical problem, we can write P1 V1 equal to P2 V2. This is the general thing for the Boyle's law. Okay. Now let's talk about the Charles law. According to Charles law, the volume of a gas is directly proportional to temperature when number of moles and pressure remains constant. So the graph between volume and temperature is a straight line. And at temperature 0 Kelvin, that is minus 273 degrees centigrade, volume becomes 0. Okay. Remember 0 degrees centigrade equal to 273.15 Kelvin. In numerical problem, V2 upon T2, we will write V1 upon T1. Now let's talk about the Gay-Lussac law. According to Gay-Lussac law, the pressure of a gas is directly proportional to its temperature. And at temperature minus 273 degrees centigrade, pressure becomes 0. The graph between pressure and temperature is straight line. For numerical problem, we will be writing P2 upon P1 equal to T2 upon T1. This temperature will be in Kelvin. Now let's talk about the Dalton's partial pressure. When in a container we put many gases which are immiscible, then if this P1 is the partial pressure due to first gas, P2 is the partial pressure due to second gas, and P3 is the partial pressure due to third gas. Okay, then we can write P total will be equal to P1 plus P2 plus P3, where P1, P2 and P3 are the partial pressures due to individual gases and P is the total pressure. Okay. Now let's see about the Gram's law of diffusion. The rate of diffusion is inversely proportional to square root of density. The graph between rate of diffusion and square root of density is a hyperbola. Now, dear student, we will be studying average velocity, average speed, RMS speed, mean speed, when and which formula is applicable, that we will see today. Okay. Dear student, in KTG model, we will solve the problem in two cases, when number of molecules are small and when number of molecules are large. Okay. So let's see. When number of gas molecules are small in the sample, okay, then how we will solve the problem? Let us assume this is a list of number of gas molecules and this is their speed. If in a gaseous sample for N1 gas molecule speed is V1, N2 gas molecule speed is V2, N3 gas molecule speed is V3, then we can write average speed equal to N1 V1 plus N2 V2 plus N3 V3 divided by N1 plus N2 plus N3. This is how we will write average speed. Now, how do we write RMS speed? That is root mean square speed. Okay, root mean square speed. This will be writing N1 V1 square plus N2 V2 square, N3 V3 square divided by N1 plus N2 plus N3 under root. This is how we will be writing root mean square speed. And how do we write most probable speed? Most probable speed. Most probable speed. The speed possessed by maximum number of gas molecule. The speed possessed by maximum number of gas molecule is called most probable speed. Okay. Speed possessed by maximum number of gas molecules is called most probable speed. Okay. And when number of gas molecules are large, like in when number of gas molecules are large, that is in KTG model. In KTG model, we will solve problem like this. RMS velocity, this is equal to under root 3 RT upon M. M is molar mass, equal to under root 3 KT upon M. K is Boltzmann constant and small m is the mass of one gas molecule. Most probable velocity, this is under root 2 RT upon M, and average speed, this is under root RT upon pi M. The ratio we can write like this: V RMS, V most probable, V average. Their proportion is under root 3 is to under root 2 is to under root 8 upon pi. This is their proportion. Okay. Dear student, V RMS is more than V average is more than V most probable. Okay. So now let's start solving some problem. The velocities of 10 particles in meter per second are 0, 2, 3, 4, 4, 4, 5, 5, 6, 9. Calculate average speed, RMS speed and most probable speed. Very simple. Average speed 0 plus 2 plus 3 plus 4, 4 means 12, plus 5, 5 means 10, 6, 9 means 15, divide by 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. 15 plus 10, 25, 25 plus 5, 30, 30 and 42, divide by 10. So answer will be 4.2 meter per second. This is the average speed. What is RMS speed? That you can easily calculate. N1 V1 square, N2 V2 square plus N3 V3 square plus 2 into 4 square. Sorry, 3 into 4 square. This number is 3. 3 into 4 square plus 2 into 5 square plus 6 square plus 9 square, divide by total number of molecule 10 and take the under root. This is RMS speed. And what is most probable speed? Directly speed possessed by maximum number of molecule. See, this is the case. 3 molecules are having speed 4. So most probable speed is 4 meter per second. So this is the answer to our problem. Okay. Now, dear student, let's see some more problem. See, just read the question. You can easily find by applying V RMS equal to under root 3 RT upon M. Okay. So very simple. The RMS speed of nitrogen molecule of the gas at room temperature is 500 meter per second. Okay. Then RMS speed of the hydrogen molecule at the same temperature. Okay. Very simple. V RMS equal to under root 3 RT upon M. Now, temperature is same. So RMS speed is inversely proportional to molar mass. So 500 upon V equal to what? RMS speed of nitrogen molecule means 28. RMS speed of the hydrogen molecule, this is 2. So this will be how much? This will be 1 upon 14. So V is what? 500 into 14. So approximately this is how much? 4 means 2000. Lesser than 2000. Okay. Under root 14 will be approximately equal to, this will be, if we take 3.8 means 3.8, this will be equal to 8 into 8 64, 8 into 3 24, 630. Then this is 3 into 8 24, 3 9 11. So this is 4 4 4 and 1 14 point something. So we can take 3.8. Okay. If we take 3.8 means 500 into 3.8 means 500 into 3.8 means what? Approximately 1900. Okay, so answer is option second. Option second is the correct answer. Okay. So dear student, in our case, correct answer is option 2. A sample of gas is at 0 degree centigrade. The temperature at which its RMS speed of the molecule will be doubled. 0 degree centigrade equal to 273 Kelvin. Okay. Dear student, RMS speed is proportional to under root T. Okay. For increasing the RMS speed to double, the temperature should become 4 times, okay? 4 times means 273 Kelvin into 4. This becomes how much? 1092 Kelvin. If you take into Celsius, subtract 273. This is 819 degrees centigrade. So correct answer is option 3. Option 4 is the correct answer. So dear student, this was some important point about the various types of speed. In the next lecture, we will be looking for important postulates made in the kinetic theory of gases. Okay, thank you.